Hi, welcome back. This is the second lecture of week 3. So we've talked about metallic bonding. Now we're going to get into molecular orbital theory and apply that to metallic bonding. What we're going to see is we're going to see where electrons reside in metals and why it's different than the octet rule and covalent bonding that we're used to from nonmetals. All right, so let's get started. All right, so molecular orbitals and metallic bonding. Um, the first thing is, what are molecular orbitals, right? So molecular orbitals are when valence orbitals, so valence electrons that reside in valence orbitals, right? So these are the 1s, 2s, 2p orbitals that you guys learned about in Gen Chem 1. Valence electrons combine in order to create molecular orbitals. All right. And molecular orbitals come in 3 flavors, right? They can be bonding, they can be non-bonding, or they can be anti-bonding. And so what these things mean. So bonding orbitals are generally going to be stabilizing. They're going to make the molecules more stable, excuse me. Non-bonding orbitals are going to be things like lone pairs, right? So these are just kind of the electrons in a molecule that don't get associated with bonds. And then anti-bonding orbitals are generally going to be destabilizing, right? So the more electrons we have in anti-bonding orbitals, the less stable our molecule is going to be. So what does this look like in covalent bonds, right? So let's take a very simple example. We'll stick with chlorine because I've been using chlorine a lot, right? So chlorine is very nice. We have all these non-bonding electrons, lone pairs, lone pairs, lone pairs, right? But we also have this covalent bond in between them. So what does that look like? So chlorine has, in the 2p orbital, chlorine has a single electron in one of them, right? Because it has 7 valence electrons. And if we bring another atom of chlorine around in the 2p orbital, we have 1 electron in that one as well. And so what happens is these two chlorines want to satisfy their octet, and so they're going to come in close contact with each other. They're going to share these electrons with each other. Now, the consequence of that is that we're going to create 2 new orbitals. So there's going to be 1 orbital down here. This is going to be our bonding orbital. And there's going to be 1 orbital up here. And this is going to be our anti-bonding orbital. Right, I'm leaving off all the non-bonding orbitals because those are just lone pairs. So there are obviously more than just these 2 electrons in here. But the non-bonding orbitals essentially don't really do anything. Right, so these two come together. Da, 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 da. And then notice that there's a gap here, and I've drawn that on purpose. We can think of this being graphed in terms of energy. And so the lower energy bonding orbital is going to be where electrons are going to want to exist, right? They want to be in the more stable position, the lower energy position, and all of that good stuff. And so we put the electrons in the bonding orbital, 2 electrons in a bonding orbital equals a covalent bond. Right? Now, notice that there's a pretty large gap, right? So in covalent bonds, there's a large gap between bonding and antibonding. Between bonding and antibonding. Right? And so it's not easy for the electrons to jump from bonding to antibonding. In order to do that, right, then we would no longer have 2 electrons in our bonding orbital, and our covalent bond would be broken. So that doesn't happen very often, right, in covalent bonds. We don't usually break covalent bonds just spontaneously. Right? What happens when we get to metals? Now, you can probably already kind of predict what's going to happen. I'm going to jump back to aluminum. Right, aluminum is a 3p, right, is going to have a single electron in its 3p orbitals because it has 3 valence electrons overall. I'm going to imagine that we have a whole bunch of aluminum atoms. Let's say we've got 9 aluminum atoms on this side, and we're going to have, well, let's say we'll just stick with 9 on this side as well. 9 aluminum atoms on this side. Now, remember that aluminum doesn't have a specific, specific molecular formula because it just kind of associates a whole bunch of them all at once. I'm going to use, let's see, we'll have 5 electrons in each one of these sides, right? Aluminum has a bunch of 3p orbitals. Some of them are going to be empty. Some of them are going to have an electron in them. We're just kind of choosing at random what we get here. When these combine, what happens with metals is that you end up with, so we have 9 and 9, so we're going to end up with 9 orbitals in the middle here. 1, 2, 3, 4. And we're going to end up with 9 up here. So same deal, bonding down here, anti-bonding up here. And we have 10 overall electrons in the bottom bonding orbitals. Now notice the energy gap that I've drawn here, right? Again, this is all, energy, right? The energy gap that I've drawn between the bonding and the anti-bonding orbitals is much, much smaller. And this is generally true for metals, right? Metals have a smaller gap between bonding and anti-bonding orbitals. Okay, so this is just kind of, if you do the math, so all of this is math based. If you take physical chemistry or do a bunch of physics, you'll eventually come across molecular orbitals and how we calculate all this stuff. So I'm kind of giving you the short version of this and just saying the gap is smaller. Trust me on this one, right? But there is more to it, and we can prove scientifically that the gap is smaller for metals. And part of it has to do with how many electrons are there. It has to do with how far down the periodic table they are, electronegativity, all this other stuff. So let's compare. We have large gap for covalent bonds, right? Which means that it's hard to have electrons go from bonding to antibonding. If we have a small gap here, it's much easier for electrons to start in the bonding and then end up in the antibonding. All it takes is a little bit of energy. Right? So we have, because metals tend to have a lot more atoms, right? I have 9 here, but in reality, it's going to be billions upon billions of atoms that are associated in a sheet of aluminum or aluminum wire or something like that. So we have these massive numbers of orbitals that we have to deal with. So in this case, we give different names to the group of bonding orbitals and the group of antibonding orbitals, right? So the group of bonding orbitals is called the valence band, right? So think of like you've got thousands upon thousands of these bonding orbitals, right? And they're all kind of combined in the same more or less energy, right? They can't all be exactly the same, but they're in the same neighborhood. This is called the valence band. Same thing with the antibonding. We've got thousands upon millions of antibonding orbitals. This is called the conduction band. And so what happens when we apply any kind of energy, and we can think of this, I'm going to suggest electrical energy just because that's where we're going with this, right? If we apply any kind of energy to this group of aluminum atoms, what's going to happen is the energy is going to pop one of these electrons from the bonding to the antibonding, from the valence band to the conduction band. And what happens in the conduction band is that we are no longer in bonding orbitals, right? So these are non covalent orbitals. Okay, so hopefully this sounds familiar, right? Now, once electrons are into this antibonding orbital, this conduction band, the electrons are free to move, right? They are no longer associated, they're no longer held in any kind of a bond. Instead, they are the antibonding, and they're free to move around, right? And so when you apply energy to metals, all of a sudden you liberate all these electrons and they are free to move around. This is conductivity, right? The reason that we call this conduction band is that metals conduct electricity because when you apply energy to a metal, it jumps electrons from the bonding orbital to the antibonding orbital and allows us to kind of to see those electrons moving around the metal, right? Which is current, which is conduction, which is conductivity. Right? And so this is just another example, another way to kind of look at this idea of um, non-covalent bonding, metallic bonding, that again explains a physical property of metals. Metals conduct electricity because they have these empty conduction bands that are easily accessible because the gap between the conduction band and the valence band is very small. All right, so that's that. Next time we're going to talk about what happens if we have, how do we control that gap? What if we make that gap a little bit bigger and make it a little bit harder for electrons to jump from one to the other? And the answer is that then we get semiconductors, and that's how you make all kinds of electronics and stuff that we use every day. So tune in for that. I will see you again soon.